let's talk about the conservation of energy tutorial. In this tutorial, the first part consists of 3 different systems of blocks that are being pushed, and we're going to look at the work done on these systems, the external work done on the systems, and changes in potential, kinetic, and total energy. In system 1, there's 2 blocks that are connected by a spring, and you apply a force on each block inward. So the block on the right experiences a force going to the left, the block on the left experiences a force going to the right. And they have a displacement equal to, they write it d0. So this displacement has a value of d0. And when these blocks move through that displacement, they end up squished together, that spring is compressed, and there's no final speed at the end. In system 2, the blocks don't have a spring. They're being pushed by the same force over the same distance, and at the end, they are moving. The final speed in system 2 is not 0. And system 3, there's a spring. This time the spring is softer or squishier than in system 1. And again, the blocks are pushed with the same force over the same distance, so that at the end, the spring is squished, but they are moving. They do have some final speed. So let's answer some of these questions. In part 1A, we're asked to fill out this table. So for system 1 and system 2, we want to look at the change, or we want to look at the sign of several different quantities. First one is the net external work. The next quantity is the change in kinetic energy, delta K. Then the change in potential energy, delta U, and finally the change in total energy. Now I'm using the symbols that the tutorial uses, K for kinetic energy, U for potential energy. Those are just other symbols that mean the same thing as KE and PE. Now, the first thing to notice is that because of the definition of work, all 3 of these systems have the same amount of external work done on them. That's because for all of these, there's the same amount of force, F0, pushing over the same distance on each block. And for each block, the force is in the direction of the displacement. So the work is positive on each of the blocks. In fact, we could write the value for the net external work done on each of these systems. It's F0 times D0, the displacement, times 2, because it's done on each of those blocks. And that's a positive number, again, because the force is in the same direction as the displacement on each of the blocks. Just to be extra clear, if you look at the block on the right, the force is to the left, the displacement's to the left, so those 2 vectors are in the same direction. The block on the left has the force to the right, it has the displacement to the right, those 2 vectors are in the same direction. So it's positive work. Now for system 1, the kinetic energy does not change. The blocks start out stationary and they end up stationary. For system 2, that change in kinetic energy is positive. The blocks start out stationary and they end up with some final speed. Potential energy, the change in potential energy for system 1 is positive. The spring starts out at its equilibrium length and it ends up compressed. For system 2, there is no potential energy to worry about. There's no spring involved. And for all of these, the motion is happening horizontally. So there's no change in gravitational potential energy. We didn't even bother writing that down. So the change in the total energy of the system is positive for each of these two cases. Okay. Now in part B, it says consider the student statements. One statement is right and two of them are wrong. Student 1 says the net work done on a system is always equal to the change in kinetic energy of that system. Student 1 is incorrect. You can see that for system 1, we had work and it gave us no change in kinetic energy. Instead, it changed the potential energy. Student 2 says the total energy of a system can change if something is doing work on that system. The net work done on a system by external forces is equal to the change in total energy of the system. Student 2 is correct. That's exactly what we just showed here in this table. The net external work gives you the change in total energy of the system. Student 3 says in the absence of friction, the total energy of a system must remain constant. That's only true if the system is closed, if there are no external forces acting on it. These systems here are not closed because the systems consist of the blocks and the springs, and there are objects external to the systems, namely the hands, that are providing external work. So student 3 is wrong because student 3 should have said in a closed system energy is constant, but if the system is open, if there are external forces acting on it, like the hands in this case, then the total energy can change. Okay, second page. A fundamental principle of physics is that the total energy of a system changes only through interactions with objects outside that system, like we just said. So the net external work on a system equals its change in total energy. And that's known as the principle of conservation of energy, because if your system is closed, by definition, the external work is zero and the total energy doesn't change. All right, here's question C. We're now including system 3. So remember, in system 3, we're pushing with the same amount of force, the same displacement. That means we have the same work, external work, as before. But now the spring is squishier, it's less stiff than in system 1. So we end up with both potential and kinetic energy. All right, so let's rank, in part C, question 1, the 3 systems according to the absolute value of the net work done by external forces. Well, this is kind of a trick question because, as we already decided, the net external work is the same for all 3. They all have the same amount of external work done. In question 2, we'll rank the 3 systems according to the absolute value of the change in total energy. Now, once again, this is kind of a trick question because, as we have just learned, the change in total energy equals the net external work done on the system. So if all 3 of these systems have the same net external work, they all have the same change in total energy. They're all equal. So the total energy change is the same in all three of these situations. The external work done is the same in all three of the situations. But the way that that work gets compartmentalized into kinetic and potential energy is different for each of the three systems. It's just split up into different amounts among kinetic and potential. So let's see which system has the biggest change in potential energy and rank all three of them. So in system 1, when we did that work on those blocks and squished the spring, all of that work went into squishing the spring. None of that work got turned into kinetic energy because V final is 0. So in system 1, we can assume that the external work equals the change in potential energy. So system 1 will have the greatest change in potential energy. System 2 had no change in potential energy. There wasn't any potential energy at all to deal with. That one's going to be last. System 3 is somewhere in the middle because we can tell that this spring is squishier, and after we do that same amount of work, these blocks are moving with some speed. So some of that work got turned into kinetic energy as well as potential energy. Oops, that's number 3. And last place was system 2, because it didn't have any change in potential energy. Now rank the three systems according to the absolute value of the change in kinetic energy. Well, system 1 is going to be last. Didn't have any change in kinetic energy. System 2 will have the greatest change in kinetic energy because all of the work done got turned into kinetic energy. System 3 is somewhere in the middle because some of that work turned into potential, some of it turned into kinetic. System 2 wins. System 3 is second place, and system 1 is last place because it has no change in kinetic energy. So is it possible to rank the three systems according to change in total energy if we're given just the rankings according to change in potential and kinetic energy? So if we only had these things, if we only had questions 3 and 4, could we figure out 2 without knowing 1? This is one of those tutorial questions that's more complicated than it really needs to be. But the idea here is that you need to know this fact that the work done is the same for all three. That implies that the change in total energy is the same for all three. You wouldn't be able to assume that just based on the potential and kinetic energies alone, because these don't tell you the amounts of potential and kinetic energy. They just tell you their relative rankings. But this statement about the work now constrains the system of equations and lets you say for sure that the total energy changes for all three systems are the same.